Evaluating machine learning generalization for elastic modulus prediction across material classes. Modern engineering relies on selecting materials with specific mechanical behaviors for structural, mechanical, and functional applications. These behaviors are governed by material properties, which determine how materials respond to applied forces and environmental conditions. Being able to determine these properties is critical for safe and efficient material selection. Traditionally, material properties are obtained through experimental testing techniques such as tensile testing and nano-indentation-based methods. While these approaches are accurate, they are often time-consuming, expensive, and destructive, particularly when evaluating large numbers of candidate materials. These limitations make large-scale material screening challenging and limit the speed at which material discovery can be advanced. Machine learning offers an alternative approach by learning relationships between known material descriptors and material properties. Prior research has shown that machine learning models can perform well when trained within an individual material class. However, most studies rely on narrow datasets and do not explicitly test whether a single model can generalize across fundamentally different material systems. This raises the question of whether machine learning models can capture more broad trends that extend beyond a single material class. The objectives of the study are threefold. First, to evaluate whether a single model can meaningfully generalize elastic modulus predictions across multiple material classes. Second, to compare the model's performance against a non-learning baseline predictor in order to verify that true learning is occurring. And finally, to identify class-dependent trends and limitations that reveal where the model performs well and where additional material-specific information may be required. To train the machine learning model, I created a dataset of 30 representative engineering materials, consisting of polymers, metals, and ceramics. Material properties were compiled from literature sources such as MathWeb and standard material handbooks. The input descriptors used were density, Poisson's ratio, and material class, all of which are physically meaningful and broadly available. Elastic modulus was used as the target output for model prediction. The dataset was analyzed using Python and the scikit-learn library. A random forest regression model was selected as the machine learning model for this project due to its robustness to small datasets and its ability to capture nonlinear relationships without strong assumptions. Model performance was evaluated using a leave-one-out cross-validation strategy, where each material is predicted using a model trained on all remaining materials. Prediction accuracy was quantified using mean absolute error. This figure shows predicted elastic modulus values compared to known literature values. The clustering of points around the ideal prediction line indicates that the model can successfully capture key elastic trends across materials. Larger deviations can be seen at the extremes of the modulus range, primarily between 50 to 100 gigapascals and 350 to 400 gigapascals, suggesting increased difficulty in predicting very stiff or very compliant materials. When results are broken down by material class, polymers exhibit the lowest prediction error at just 1.8 gigapascals. Ceramics show moderate error at 33 gigapascals, while metals show the highest error at approximately 47.6 gigapascals. This indicates that model performance is strongly class-dependent. To confirm that the model is learning beyond just simple averaging, I compared the random forest regression model to a baseline predictor that always predicts the mean elastic modulus of the training data. The random forest outperformed the baseline by approximately 3 to 5 times on average across all material classes, which confirms that meaningful learning is occurring. Overall, this study demonstrates that machine learning models can generalize elastic property predictions across all three material classes when provided with physically meaningful descriptors. However, performance definitely remains class-dependent. In particular, metals exhibited the highest prediction error, which can be attributed to the absence of descriptors related to microstructure and processing history, such as grain size, phase composition, and crystallographic texture. Future work could incorporate such microstructural descriptors to better capture this metal-specific behavior and improve generalization across structurally complex material systems. Additionally, expanding the dataset beyond just 30 samples could provide a more comprehensive training set for the machine learning model to learn from. And finally, here are the references I used for my study. Thank you.